Today we have Steadfast Engineering, who is going to be leading a presentation on the evolution and future of steel connection design. So this is something that many people don't really realize is an area that is changing and taking more and more advantage of technologies and so on. So I want to thank Dean Anderson, Keenan Dooley, and Adam Coleman for doing this presentation today. And with that, we'll turn it over to you.
All right. Thank you, Dr. Driver. Thanks for those in the Steel Center as well for inviting us to speak. Again, my name is Dean Anderson. I'm the founder of Steadfast Engineering. And joining me as well is Adam Coleman and Keenan Dooley. They're both engineers that work with me here at Steadfast Engineering. What we're going to be talking about today is three primary things. We're going to start with really the evolution of the company. I kind of wanted to touch on that a little bit and talk about how Steadfast Engineering started. Talk a little bit about how we fit into the construction world. If I understand, a lot of these people listening will be students. And I remember back when I was a student, I didn't really know a lot of that stuff. I didn't know how, my things that I was learning in school would apply in real life setting. So we're going to talk about that a little bit and talk about how the company started. Then we're going to narrow it down to a particular connection that we've been working on to show how a connection can change and how the process of design works. Again, when I was in school, when I was taking engineering, I didn't really realize, I just thought they give you the information, you design the connection, you're done. It's that easy. But in the real world, it's not necessarily that easy. So we're going to go through one of those connections that's pretty interesting for us to do. And then we're going to get into evolving into the future. So Adam at that point is going to talk a little bit about some of the things that might be coming in the future with respect to connection design. I'm going to offer, if anybody does have any questions, feel free to add those in the chat with Zoom. We're going to have a section at the end where we're going to answer some questions, and that might be an easy way for you to kind of put your thoughts down as the presentation is going, and we can go through those and answer those things at the end. So I'll start with the company, the history of Steadfast Engineering. It started in my tiny little brain way back when I was still working. I took 10 years off. I graduated from high school and I started just working. And took about 10 years out of high school before I went back to university. And it kind of started with a friend of mine who was a structural engineer. He had a company, he was working out of his basement, and he showed me some of the things that he was doing and some of the things that he had to figure out. And it really interested me. And it kind of got me thinking that, hey, I want to do the same thing too. I'm going to start my own company eventually. So I went back to university, or I went to university for the first time, and got my bachelor's degree and graduated in 2006. Dr. Driver here is one of my professors for that. And then went back again, continued with school, and got my MEng in 2010. Again, Dr. Driver was one of my professors for that. And both of those were at the University of Alberta. So I was working in the co-op program, the civil engineering co-op program, and I got hired by a structural steel fabricator. Fabricator, I'm going to use that word a lot. That's a company who makes the steel. They're the ones, or if you have a steel building, they're the guys who cut it, weld it, put it all together, put it up in the field for use. And this fabricator hired me, and I was primarily doing structural steel connection design. That was my job. And as I was working through that, I started realizing, well, I want to do a little bit more. I want to see about designing some concrete, maybe doing some residential construction. And thought maybe the best way to do that is to incorporate. So I incorporated in 2011, created my company called Steadfast Engineering, again, with plans of just doing a little bit more than structural steel connection design. One thing I was doing also with that fabricator was erection plans. So those are the plans where as the building is being constructed, I check and make sure to see if they need temporary bracing in certain locations, the order in which it's put up so it's still safe during construction. And other fabricators started hearing that, hey, you know how to do erection plans? There's a big need for those at the time, and it was kind of a new thing. So they hired me to do these erection plans. Then they started hearing, what, you do connection design too? There's a huge demand at the time for connection design engineers. And so I started subcontracting myself to these other fabricators too. And so it's kind of funny how the company did evolve in that way. The services provided really changed. I initially was planning on doing stuff other than connection design, and it kind of switched back to doing pretty much, I don't know, right now we're doing probably 80 to 90% of our work is connection design. We also do some other engineering work. We do erection plans for buildings. We do some what we call structural steel designs. That's designing the superstructure of a building, the beams and the columns and the bracing. Do a little bit of that and do a little bit of what they call miscellaneous steel design. So that's all of the stuff that's kind of stuck onto the building. So the stairs, maybe platforms, little things that are kind of stuck on the building, handrails, little things like that onto the building. So we do some design that way. So over the years, again, I founded it in 2011, so we're about 9 years old right now. Over the years, kind of grew really slow. It was a one-man show for quite a while, and then hired one engineer, then hired two engineers, and that's where we're at right now. And I really had to learn the business operations on the fly. That's actually a pretty big challenge to try to figure out, how do you do payroll? How do you make sure your taxes are paid? How do you make sure everything's okay, kind of with the government, the GST, all that sort of stuff. So it's kind of interesting to learn all that on the fly through trial and error. And that actually led to my next kind of step where I'm going back to university this fall to take my MBA part-time to hopefully learn that side of the work a little bit better so we can be an even better company. Like I say, we do primarily right now structural steel connection design. Again, when I started, I was doing it primarily locally in the Edmonton area, in the Alberta area. Now we provide services basically across Canada. Primarily in Western Canada, BC, Alberta, Saskatchewan, do some stuff in Manitoba, Ontario, Northwest Territories. But we kind of spread out. We've grown, we've evolved over this period of time. So how do we fit into the construction world? How do we fit into the construction process? Again, when I was in school, I didn't really understand how this worked. Again, if the people listening have been through engineering, they might understand this a little bit more than others, a little bit better than others. So I'm going to give kind of a simplistic summary of how this whole thing works. So it all starts with some guy. He's dreaming up a building in his head, and he's got lots of money. So he wants to build a building. He wants to make this thing. But in his mind right now, it's just an idea. Similar to the way I started the company, it was just an idea, and I had to put it together. He's got money and an idea, and he wants to build a building. So what he does is he hires an architect to try to turn his dream into reality. He talks to the architect. They talk about the use of the building, where they want the walls, the floor plan, all of those things that are involved in what his dream is for what this building is going to be. And they come up with some two-dimensional drawings and a 3D model in general for this. So they come up with this stuff. Then they talk to a structural engineer. Structural engineer is there so to make sure this dream that they have doesn't fall over when the wind blows, when the snow falls, all those sorts of things. And the structural engineer, I'm going to interchange some terms, probably not on purpose, throughout this presentation. The structural engineer is often called the engineer of record. You might even hear us say EOR, and that stands for engineer of record. But the structural engineer is the guy that he figures out how to make sure this building doesn't fall over. So he designs the foundations. He designs the structure that fits inside what the architect and the owner have come up with. And he makes sure the building is safe. And all this information is summed up into 2D drawings, so two-dimensional drawings. Oftentimes during this process, there's three-dimensional drawing or models made, and then they put this information onto two-dimensional drawings, and they put this project out, this building that's been dreamed up, what they call out to tender. So they put it out into the world, and they give it to all these contractors, the people that build the steel, like the fabricator, concrete guys, cladding guys, the guys that put the skin on the buildings, guys that build the roof, all of those different trades that are involved in building a building. They put together their price. They say, you have to pay us this much for us to do that part of the work. And they select fabricators. So a fabricator, we're going to narrow down onto the fabricator. He's the guy who builds the steel. There's a detailer involved here too. The detailer sometimes works separate from the fabricator. Sometimes they work for the fabricator. The detailer is a draftsman. It's a specialized draftsman, actually a highly skilled career job. They specialize in structural steel, and they take that information and they create, basically, if you've ever bought something from IKEA and you have an IKEA booklet, they create drawings to show how this building should be made. They build that IKEA booklet so then the fabricator can build the steel, and they have these drawings that are created. So the owner, the architect, they hire the fabricator. Detailers involved too. They might hire a detailer as well on the side. So they hire this fabricator, and they need an engineer. Up to this point, only the steel columns, the beams, the bracing, just those members have been designed and not the connections. Again, this is in general, and they delegate this connection design out to the fabricator. The reason they do that is because oftentimes the fabricator has specific processes in their shop. They have certain ways that they want to put it together in the field. And so it doesn't really make a lot of sense for the structural engineer, the guy who designed the beams and columns, to specify a bunch of very precise, exacting connections that really restrict what the fabricator can do. So they delegate that design out. So that's when they hire Steadfast. They hire us, they say, hey, we want you to design these connections for us to suit our processes, to suit our erection procedures, the way it can be built in the field. And we have to bridge that gap. That's our job. We have to try to bridge that gap between the fabricator, what they want to build, what their shop can do. We have to look at what the engineer of record, the structural engineer, has provided as far as loading goes. He gives us those loads that we have to connect the connection for. We have to look at what the architect has in mind. He wants to make sure it looks a certain way. And we have to balance all of these things. We have to balance all these things between all these different parties to come up with the best connection. So we have the job. We're pretty happy about that. And how do we get it done? What do we actually do? The first thing that we do is go through those two-dimensional drawings that are created by the structural engineer and the architect. And we try to figure out, in general, what are the best connections for this. And that goes back to the fabricator. What can he build? What is he used to building? What does he want to do? There's many different ways to connect steel together. In this example here, we have two beams, two wide flange beams. I-beams is what they're referred to also. And in this case, they're connected with bolts. They have an angle, L-shaped piece, and they're bolted together. So that might work for a certain fabricator, but another fabricator might want to do something like this, where you have one beam here, another beam here, and they have a steel plate that's welded to this other beam with bolts. So in this case, if this guy with all these bolted connections, if he has the processes, he has the automation, the machines to cut this beam, to drill these holes, then he's going to prefer this connection. If this guy over here doesn't have that equipment in that way, but he's got lots of welders, he would maybe prefer to do this connection. So we have to discuss that with the fabricator and figure out what they want to do so that we can design the best type of connection for them. Same thing applies to bracing. Right here we have a diagonal brace, the corner of one, we have a beam and we have a column. This is what they call a gusset plate that's attaching all these things together. Right there you see a little tiny bolt, and that is actually an erection bolt. They use that bolt to put everything in place in the field, and then they have to come in on site and weld along these edges. So that's what they call a field welded connection. They might not want to do that. They want to say, no, we don't want to weld in the field. We don't want to mess around with that. We want to maybe bolt it in the field. So they want to maybe do this connection where it's bolted. So we talk to the fabricator. We figure out what they want. And then a lot of the time, we have to keep in mind what can actually be done with respect to the loading. If you're in an earthquake zone, if you're out in BC where earthquakes are a lot more prominent, and you have to design the connections to resist those loads, this connection here that's welded would be much more suited to that type of situation. So we have to balance all those things. We might have to go back to the fabricator and say, well, no, we can't really do this really small bolted connection. We have to make it a little bit bigger and beefier so that we can accommodate the loading. So we can have that back and forth to accommodate those sorts of things. So then we design, we figure out what we have to design, we put it all together, and now we have to communicate that information to the detailer. Again, he's the one who's going to create that IKEA booklet, the assembly instructions for how the steel is made. And what we do, first of all, is we take the two-dimensional drawings created by the structural engineer. I took a little snapshot from one of those drawings. So we have these black lines. That's created by the structural engineer. This is what they call a top view. So you're looking down on the structure. And these lines represent beams going across. And then if you see the red in here, the red is the text that we have added to this PDF document. So we use PDF software to add these notes in. And each one of these notes kind of gives them instructions on what to do, how to connect this. Up here, you see some little text there, and that represents a connection. So we'll give a connection sketch. So we have a map to show where it goes. We have a sketch to show exactly what they have to do at that location. So this is what is in the middle here. This is a sketch that shows exactly what's required at that spot. So we have a plate. We have the number of bolts, all the dimensions. You probably can't see them because it's small, but those are all dimensions to show down to the millimeter how this thing is put together. We have it all welded together in a certain way, make sure the welds are big enough. And the detailer takes that and he creates and puts that into his 3D model. So again, the detailer creates a 3D model. From that 3D model, he creates two-dimensional shop drawings. He creates that little booklet of how this thing goes together. So in this case here, we have our sketch and we have the actual connection right beside it. This is how it looks like when it's put in the model. So we give that information to the detailer and he creates his three-dimensional model and his two-dimensional shop drawings. A little snapshot here of kind of an overall model. Again, they're building this model in three-dimensional space down to the millimeter. They got all the welds, they got all the bolts, they got all the plate thicknesses. If you're to zoom right into one particular spot of that model, it shows exactly what's going to look like in real life when the whole thing's done and built in real, in person. So they create this 3D model, create the two-dimensional shop drawings. This is, again, a kind of a small snapshot, but it's kind of an idea of what one of those shop drawings looks like. This is the piece of paper that the welder is going to take out, the fabricator, I guess, the guy who drills the holes, welds the steel, measures everything up, make sure that piece is built correctly. He takes that onto the shop floor and he builds that piece. Then we go in and we've communicated to them designs. They've created their model, they've created their two-dimensional shop drawings. And then we have to go back and we have to make sure that those drawings reflect the designs that we provided. So we go through and we check all of these drawings. In the world where we have to take responsibility for our designs, these two-dimensional drawings are the things that we are signing. Those are the things that we're sealing. We're saying that, yes, these designs reflect what is designed according to code, what is safe. And that's one thing that Adam, I think, is going to talk about a little bit later on, is about how that is maybe not the most efficient way to do things, and there hopefully can be some improvement in that, but that is the way it's done right now. These two-dimensional drawings are kind of that legal document to say, we designed this, and it's done according to code. So now we're going to narrow down onto a particular connection. We were working on a project called the South Burnaby Ice Arena. So again, this snapshot probably looks familiar. It's from earlier. But this is a big zoom out of this project we were working on. And to get an idea of the scale, this is 2 hockey rinks along with seating. So it's got the bleachers on the side surrounding the rink. And there's another one down over here with some other rooms and structure in between those 2 rinks. So that's the overall building. We were working in this project with MSC, that's McDougall Steel Erectors, and they are the fabricator. They're the guys who are building the steel. They're located in Prince Edward Island. Exact Detailing is the detailer. They're located in Victoria with offices across Canada. Their home office is in Victoria. And so it really shows how the virtual world works and how we can work kind of across the country to accomplish one project in one particular location. We're spanning across the whole width of Canada essentially in this one project. And it works really well. We have a lot of the tools that can make this happen quite effectively. So we've got 2 hockey rinks inside the facility. And what we're looking at is these triangular shapes here. There's 2 here and 2 down here. We're going to focus in on one of these triangular shapes. Those are trusses. These trusses support the entire roof that clear spans over top of these rinks. They span diagonally, so they're extra long. And in between, hopefully I don't offend people at the steel center, is a wood structure. This is actually a hybrid steel wood structure. There's a whole bunch of wood members that span in between there to make up the roof. So we're going to look at one of these trusses. Each member or each part of that truss is a huge cord member. These things span very far, and so they're constructed from these massive sections. The designation of it is a W1000 by 883. What that represents is this thing is 1 meter tall, 1,000 millimeters, and it weighs 883 kilograms per meter. So it's quite large. To give an idea of scale, if you're a person standing beside this beam, it comes up probably roughly 2/3 up to your body. So quite large, quite high. If you look at one of the flanges, so a flange is the horizontal parts of this wide flange shape, it's about 3 inches thick. So if you hold up your hand and you go from knuckle to knuckle, that's about 3 inches. That's how thick the steel is on the top and bottom flange. This web part here is about 2 inches. So it's a very thick, very heavy member that we had to deal with. This is a snapshot of one of those trusses, and it was pretty challenging. They are very long, 46 meters. So if you imagine a football field, this thing would span half of that football field. So it's quite large. So it presents a lot of challenges. They're so long, so it creates these challenges about how to ship it. How do you get something that's half a football field long to site? How do you build this in your shop? How can you effectively put this together in your shop? You'd have to have a shop that's, you know, more than a half a football field long just to accommodate that. So it's quite challenging. So what we did is we figured that you had to put splices in here. This is, again, talking with the fabricator, talking with how are we going to do this? So what we did was we figured that we needed to cut this truss in third parts. So we got 3 separate sections of truss. It's actually 4 because this top part is separate and that part is separate too. But we're basically cutting this truss into thirds. So we have to cut this. So what we had to do was go back to the engineer record. We have to say, okay, we want to cut this truss because it's too tough to get to site. It's too tough to actually put together. So give us the loads. And we again went back and forth a little bit with the engineer record to come up with the best loads. Sometimes the tendency is to give really safe, really high loads. We had to kind of go back and forth to try to get the best loads so we could design the best connection possible that's cost effective and can be built on site, can actually be accommodated. So this is where we come in. This is where Steadfast comes in. There's a connection required at the splice. The engineers provided forces. We've got those. And these forces were actually quite large. We're looking at the bottom chord of a truss. So again, each truss is consisted of that 1 meter tall member. And each truss had a tension load of 10,000 kilonewtons. It had a shear of 900 kilonewtons and a moment of 500 kilonewton meters. To get a rough idea of how large that is, if you were to imagine 170, I'm going to give you very specific here, African bush elephants. 170 of these elephants is what 10,000 kilonewtons roughly is. So if you were to hang 170 elephants off the end of this thing, that's how much force is coming through this truss. So it's quite challenging to try to come up with a design that can accommodate these forces. Again, we have to accommodate the loads, we have to accommodate the fabricator, we have to make sure it can be built on site, we have to make sure the architect is happy with the way it looks, and we have to balance all these things while trying to make this, this connection. So it's pretty challenging. So at this point, I'm going to pass it over to Keenan. He was the guy that did most of the work on this particular connection. So he's going to discuss some of the first few designs that we kind of worked on to try to figure out the best way to do this. So I'll pass it off to Keenan.
Right, thanks, Dean. So now that we have these forces, we're tasked with the challenge of figuring out what can be done, what's possible here. And these are massive loads that we're dealing with. So the first concept that we came up with was a flange plate connection. In this configuration, we have plates on both sides of the flanges, as well as on both sides of the webs. The nice plus this connection is that these plates are shipped loose to the site, and then they can be easily bolted up during construction. This is also great for the fabricator, because we don't have any welding involved here, not in the shop or in the field. So this is going to greatly reduce their labor costs. And one of the primary goals for the fabricator in this job was to avoid any field welding where possible. So field welding, this can be a challenging and a costly process, as it's difficult to control the outdoor environment around the welder. So then you end up with a bit of a higher risk of producing poor quality welds, which we don't want. And they don't want to have to rework those welds as a result. It's also more difficult for them to maneuver these pieces of the truss into place prior to welding on site, compared to doing this into the shop where you have, all of your trains accessible to you. So field welding could be done, but the erector wants to avoid this if we can do that. So another plus with this is that the direction of the bolt holes allow for a small amount of adjustment in the field. So these holes are drilled slightly larger than the bolts themselves. So when they go to piece this truss together on site, it provides a bit of leeway for everything to connect up. It also gives them an easier chance of meeting the tolerances when they go to plumb the building. So although we've seen a bunch of positives here, there are also some downsides to this connection, which we'll look at next. Okay, so a few of the key drawbacks. The first issue that was encountered is that these thick flange plates that sit on top of our member are now clashing with the roof deck and the architectural finishes that they have above this member. So these flange plates are around 2 inches thick, which is quite significant, and they'll end up protruding more than compared to a typical case where you have small forces to deal with. And another issue that came up is that the bolts in the bottom flange of our member are going to be visible from below. So these trusses are exposed to the inside of the arena, and this architect didn't want any bolts to be seen by the occupants. So as an engineer, I like to think that these bolts are really cool to look at, but beauty is something that's in the eye of the beholder, and in this case, it wasn't a part of the architect's vision to see these bolts. So ultimately, for these few reasons, this flange plate connection had to be scrapped. But luckily, there's some other possibilities, and we'll take a look at another one next. Okay, so the second concept that we came up with was an end plate style connection. So similar to that first flange plate option, this is going to allow everything to be bolted on site and avoids that pesky field welding. This configuration is a little bit different though, in that we now have an end plate that's welded to each segment of the truss cords, and we also have a series of stiffeners that are required. So you can see these stiffeners in the web of the member here. So what these stiffeners are doing is they're strengthening the plate, and they're going to allow the forces to be transferred effectively to the bolts without causing a lot of prying action on our bolts, which will reduce the strength that you can get out of them. So what are the main advantages with this concept? Well, first, since the bolts are shared between the two sides of the splice, a smaller amount of bolts are required overall when compared to that first flange plate option. So in that first flange plate option, we had an independent group of bolts on each side of that connection. So overall, you're going to end up with more bolts. And then the second key advantage here is that we don't have plates that are above the truss anymore. So we're not going to have that clash that was occurring with the roof deck or the architectural finishes above. And then there's also an improved aesthetic with this look. Now the bolts are more concealed since they're above the bottom flange of the beam, and they're not going to be as easily spotted by viewers from below. So with those few improvements, it seemed like we're going in the right direction now, but there were some other issues that arose, and we'll take a look at those now. So the first downside with this concept is the amount of welding that's involved. So each of these end plates and each of these stiffeners are going to need to be welded to the cord segments. And although this is something that's going to be all done in the shop, it's still going to add a lot of work for our fabricator. The size of these welds are quite large, and they require multiple passes by a welder. So you're going to have to go back and forth over the length of this weld to complete it. Another downside with this concept is that we now have to pre-tension the bolts. With this configuration, the bolts are now resisting tensile loads and shear loads rather than only shear loads, which was the case with our earlier flange plate option. So pre-tensioning is something that's required in S16 or the Canadian standard. And so what this does is it reduces prying action that can occur on the bolts. It also decreases the stress range that's going to happen in the bolts. This is all great from our perspective as engineers, but it's a different story for the guys on site. Now the erector is going to have to do more work. Each of these bolts has to be tightened to a correct level of pre-tension. So it's going to take more time for them to go through each of these bolts and tighten it up the right amount. And then there's one final downside that ended up occurring with this concept, and it's another architecturally driven issue. So between the flanges of the truss cords, they want to run a sprinkler line which would go along the entire length of the truss. So this meant that when you got to these splice points, they need to somehow pass the sprinkler line through there. So what they want to do is cut this 6-inch diameter hole through the end plates. As you can imagine and see in our picture here, that's a large amount of material from our end plate. So for strength concerns, this wasn't going to work now. So once again, we're going to have to go back to the drawing board and come up with some new ideas. So I'll pass this back to Dean now.
All right, so yeah, we were pretty challenged. Those were our top two designs that we wanted to use. We had to get a little bit more creative. We had to try to figure out something that actually could satisfy all of these requirements. So what we came up with was a built-up flange plate connection. So what we ended up doing was instead we had to make sure that we didn't have anything on the top of the beam. We had to make sure that we had some room for the sprinkler line. So we ended up welding a plate that went across and then bolting that plate together. We had enough space for our sprinkler line, so it satisfied that requirement. And it satisfied the loads. We're going to look at that a bit later about how we were able to accommodate all the loads. And we also were able to satisfy that idea where the architect didn't want to see any bolts. So these little blue lines here represent some cover plates that we actually had to put over the splice deck connection to cover up those nasty, ugly bolts that nobody wants to see. And we had to make sure that all that could be accommodated. So we had to fit our connection within the profile of this beam. So again, very challenging to try to figure out how to design something that fits inside but still accommodates all of these loads. Another idea of how to understand how big this is. If you're to imagine these plates across here, they were 2.5 inches thick each. So again, if you hold up your hand and you maybe go 3 knuckles, that's about 2.5 inches. So we got about 2.25 hands And I couldn't draw that on the slide here, but that's what that represents. That's how thick this is. So it's very large, very thick, and a lot of bolts, a lot of very high strength bolts in there. That's a 3D version of the connection in the model. It shows how we have these plates that are welded to each member, and then these yellow plates span across to create that connection, that splice connection between, with connection in the middle to accommodate the shear force and also some tension force. So how it works, how this connection works overall. Again, this is for the engineers listening, which is probably most of you. This is how this connection worked. We had to accommodate the shear, the tension, and the moment. We had to make sure that we were able to resist these forces. So I kind of showing a bit of a breakdown on how we broke those forces up. We had the shear force that's resisted primarily by this web plate, or 2 web plates. We have 1 plate on each side. The tension force, we broke up into 3 components based on the cross-sectional area of these connection plates here at the top and the bottom, and then also the cross-sectional area of this connection in the middle. So we split our tension force up, that 170 elephants, into those 3 components. And then the moment we split into a couple. We designed this where the bottom flange is actually bearing in compression. These 2 beams have to be touching. They have to have that bearing at the bottom flange. So at the bottom flange they bear, so we were able to put the compression moment at the bottom flange. And then we had the other couple from the moment split into tension at the top flange. So we sum all of those things up. So this top flange connection here has to resist both of these tensions added together. This web plate connection has to resist this shear and tension combined. That force also in the bolts and the plate. So that's how we broke up the forces in this connection and made sure that it was designed appropriately so we could resist those things. And then also, hopefully, well, definitely resisting the loads and satisfying all of the other people involved. So some key takeaways from this. We had to balance the needs of everyone. The architect was concerned with how it looked. He didn't want to see those bolts. He wanted everything kind of hidden. The mechanical guy wanted the sprinkler line to go through the connection. So we had to make sure we accommodated for that. The engineers, including us, don't want it to fall down. And probably just about everybody else in that ice rink too don't want that to fall down either. So we had to make sure it's strong enough. So it took several iterations. You know, we had to go through this process several times. It's not simply what I thought in school when I was in engineering class, imagining, okay, yeah, they're just going to give me these numbers. And it's just going to be like an assignment. I figure it out and I'm done and it's done one time, finished. It's not that way. You have to keep going over and over to come up with those different solutions to the same problem so that you can accommodate everybody. So there's many different pros and cons of each solution. And this solution here appeared to satisfy everybody. So we're pretty happy about that it actually worked. So evolving into the future, we're going to go to Adam now, and he's going to talk a little bit about what we can look forward to with respect to connection design and that process in the future. Again, there's lots of things that we do maybe right now that are not as efficient as they could be. We maybe don't have the technology available to us yet. So I'll hand it over to Adam, and he can talk a little bit about evolving into the future.
Thanks, Dean. So yeah, I guess the first idea that we're going to kind of discuss is how engineering designs and construction information in general are provided between companies. As Dean kind of mentioned earlier, currently it's a 2D, 3D cycle that appears to have some steps that can be improved. So the typical process for a building usually follow these steps. So first, the engineer of record, or EOR, creates a 3D model to analyze and design the members of the building. And then his nice 3D model, he decides to compress it down to 2D structural drawings with plan views, elevations, and details, attempting to capture everything from the 3D model, which obviously it's hard to do that. So I guess, yeah, usually small items or something will get missed, so it'll end up causing extra time in the future. So once they have these 2D drawings, they're sealed and they send them out to the fabricator. And then the fabricator will take these 2D drawings from the engineer of record and create their own 3D model. And so there's usually quite a bit of back and forth as the stuff that was missed by the engineer of record going from 3D to 2D needs to get clarified. So they'll go back and forth to get their 3D model finalized. And then once the fabricator has confirmed everything and modeled in connections, they take their 3D model and again flatten it into 2D drawings for the connection engineer to seal for the shop to fabricate and for the erecting crew to put it together. So in the end, you get a 3D structure in real life, but it had many possibly unnecessary steps in between. So one option that we see potentially helping to reduce this wasted time and lower missing information is for the engineers to stamp 3D models themselves instead of converting it to 2D drawings, because 3D models better capture everything as it is. Like, it's going to be a 3D structure in the end, so why would you not stamp 3D model? That's kind of our thinking behind it. But obviously there would be some complications, as there will need to be a way to capture everything required, such as like weld symbols, general notes, design loads, but it shouldn't be too difficult to add this into the model. And it's becoming more common already for engineers to send an export of their model for comparison to aid the fabricators, but it still seems like you could improve this to the point where 2D drawings could be completely eliminated eventually. Yeah, so we'll see. Hopefully things will trend that way eventually. So we had sent a query to Apega actually about this, and they seemed open to the possibility of it. Yeah, so then our next topic is looking specifically at connection design. So the future likely includes some sort of computational design or artificial intelligence, machine learning. Yeah, and this could also be integrated within the fabricator's 3D modeling software, so that in like an auto connect type of feature. So computational and AI connection design will hopefully be able to analyze connection points and create the most efficient method of connecting them based off of parameters input by engineers or fabricators or erectors. And this could result in maximized efficiency in plate shapes and sizes, bolts, number of welds. So it's a relatively easy for simple connections to implement this, such as like shear tabs shown in the picture below. Some software, such as like Tekla Structures, can already do this for simple connections, but it hasn't been widely adopted yet, and I think it's still being developed further to make it more robust. So when connections get more complicated with many pieces involved, it becomes difficult to decide the best option for welding or bolting or like frames, and how to ship it and how it's going to be erected. So as Dean mentioned earlier, what is considered best or most practical will also depend on the people involved in the project. So some fabricators may prefer shear tabs, or others may prefer angles or end plates. Some might want bolted or welded bracing, and so on. So some erectors might have like a large crane, so they want everything from the shop to be sent in as large of frames as possible, so that they can like reduce their erection time by putting up large frames, whereas people that have small cranes that can't deal with these large frames might want everything sent in individual pieces. So yeah, this image on the bottom right there, as a current project that we're currently working on, it's a little hard to see in the picture, but there are 3 beams all connecting to one HSS column, and all 3 had to be moment connected because that column is kind of like cantilevered over an overhang, so the moment connections are to help hold it up. And then you also have 2 W brace sections coming into the same work point as those 3 moment connections. And I think the braces had 700 kilonewtons or something of axial load in them, so it's not a small amount of load, so it's pretty big. So for this connection, we went back and forth with the fabricators and erectors on what would be the most efficient method of connecting these pieces, like keeping in mind fabrication time, the shipping widths that they're allowed, and as well as the erection issues that could arise. So I think this is where the computational design or AI currently would have difficulties, is these conversations that we can have in person about what is our best option to use would somehow need to be captured by inputs or variables given to the software. which could result in many options that you need to put, which could kind of reduce the efficiency of the computational design in the first place. So yeah, currently the idea of like the computational design or AI coming up with this type of connection seems unlikely right now, but given the rate at which computers and technology are developing, it's likely not far off in the future that computers will be able to design this probably faster and better than what we can currently do. So as computers begin to determine connections on their own, I think the role of the connection engineer is likely going to shift more into checking like the background details of how the computer program is making its decisions. So we're making sure that it's capturing everything and not missing anything. There'd also likely be like kind of a human element of reviewing the computer designs, as we can look at something and know right away if it looks weird or it won't work for some reason, whereas a computer just doesn't have that. It's just going to spit out what it's believed to be is the best design and kind of just go from there. So I think there will always kind of be a human element of reviewing it to make sure it makes sense. Yeah, but I guess given all of this, when it comes to engineering, the possibilities for the future are like nearly endless, and new ideas are always emerging. So things we haven't even thought about yet, we'll probably be using in a few years. So we're very excited to see where the engineering world is headed in the next decade and even the next few years.
Yeah, thanks, Adam. So that ends our time. We're going to open it up for questions now. There's a few questions in the chat. So we had one from Taro. He's asking about the recording of it, and I believe AJ would be able to say if that's available, and I think it is. Oh, Matt said he responded to that and said yes, they'd be available. He's talking about trusses being pinned at ends and long spans. So how does the seismic area design impact design of big trusses? So moving supports, dampers, are those anywhere? So yeah, it's a good question. It really comes down to, that's where that 3D modeling is such a powerful tool to accommodate that. That's one thing we were discussing with the engineer of record with this particular truss, was when he was putting it in his model, he had, lots and lots. I'm not sure exactly how many, but there's a lot of different load cases and load combinations that are applied to this truss, seismic being one of them. And he was concerned about how we were connecting it to see if the connection was too flexible or not flexible. He said what he was asking is it fully welded, to make sure that he knew that that connection wasn't going to deflect very much. And all that came into play. So yeah, the seismic area does impact that kind of stuff. If you have that amount of mass in the roof kind of shifting around, it would have to be accommodated in the design. Kyle has a question about the sprinkler. He says, when was the sprinkler introduced? I'm not even really sure when. It was introduced to us kind of later in the process. And I don't know if we had that information before. I don't know if Keenan has an answer to that one or not. I know for us, we didn't know about it until we were kind of well along, after we gave them that end plate connection. I guess a bit of an idea of the scale of how long this whole process took. We started designing this connection in November, and we only just finished designing it recently, like over a couple of months ago is when we finished. And I think probably about halfway through is when the sprinkler got thrown in there. So I don't know, Keenan, is that about right? You can give you a thumbs up if that's about right. Yeah, so that's about right. Is about kind of about halfway through is when we got the sprinkler thrown at us. Ibukan, I'm not sure if I'm pronouncing that right, hopefully I am, said, what were the key technical standards on this project? The primary one was S16, the Canadian Steel Building Code. That was the big one. Then we have the contract documents. That's also the other big one. A lot of the time, the engineer of record will put certain restrictions, I guess, or requirements, is maybe a better word, in the contract documents that we have to fit. But primarily it was S16, which is the Canadian Steel Building Code. And Kyle has a comment and a question about, isn't one problem with lots of modeling software not having access or up-to-date Canadian codes? Which ones do you know have good Canadian code access? I know the first part of that question is some programs are good and some programs aren't. I think Adam mentioned QNect. And as far as I know, I'm not an expert on QNEC, but the last I heard was they were primarily with the American code, and they weren't quite adapted yet to the Canadian code. And then other ones too, we recently got SAP, and that has the Canadian code in it, and that's one of the reasons we did it. And there are some programs, S-Frames one, who's a part of the Steel Center, who they are a Canadian company, so they have the Canadian codes. As far as that, I'm not sure. I don't know if I'm the best one to ask which ones. You'd almost have to shop around and see which ones have the best Canadian code access. But those are the ones that we've had experience with. So,
actually, just to add, with QNEC, I was actually speaking to them last week in one of their presentations, and they did mention their next code that they're working on, like in the pipeline, is the Canadian one actually. And they were saying, roughly speaking, it might be coming out before the end of the year. That's what they're hoping for. So fingers crossed.
all right. So those are the questions that are on chat. If anybody else has any questions, feel free to go for it.
Yeah, please just turn on your microphone and ask if you have any questions.
No, Dr. Driver raised a hand. What a change. What a switch.
I just wanted to play with the technology.
Oh, okay.
Well, I guess the first thing I should say is I totally agree that bolts are beautiful. I think we got to get that out of the way, and it's sort of a body image kind of issue. We'll make that point first. But the second one was about the 3D drawings, because first of all, I shouldn't call it drawings, 3D model. Did I understand correct that you guys don't use the 3D model at all in your work?
No, we definitely use it. We use Tekla. That's the primary one that we use right now. We've also had access to StruCAD, that sort of thing.
Okay.
We use it, but we primarily use it for reference.
I see.
Again, that definitely can change. We've talked even with the guys at Exact about, can we input some of our connection codes in the model, kind of real time, I guess, in the actual model, so they can take the connections from there.
Okay.
But right now we usually primarily use it for reference. We can pull dimensions out of the model. We can see how the members line up, all that sort of stuff. But then we translate that into the sketches, into the 2D world. So.
Okay. I guess the part two of that is the whole idea of being able to seal or stamp a model. That discussion has been going on for many, many years. Like I haven't followed it very closely because it's not really a part of my world in most days. So I'm a bit surprised to hear that APEGA sort of seems to be hearing about that for the first time. Is that not already a thing?
It's not well, they did answer back, and they said that you can use the 3D PDF model, and you can stamp that. There's ways of doing that, electronically stamping that model.
Right.
I know for me, as far as connections go, I don't think I would be comfortable doing that because it doesn't show enough information, particularly the weld size. You'd have to try to get the weld size in there somehow. I'm not sure how much information and how detailed those 3D models can get in PDF anyway to represent that. So that'd be one of the challenges that I would see.
Yeah, I know it's a loaded issue, but it seems to have been being discussed for a long time. But I guess maybe that's the nature of discussions as they go on and on. Yeah. Okay. Thank you. Okay.
Yeah, actually, and just on like the PDF point or stamping a 3D model inside of a PDF, I think that somewhat defeats the purpose as well. Like I think APEGA should be looking at a way to stamp an actual model in software of some sort, because stamping it in 3D PDF would only allow you to view it in 3D, but the information you would have to recreate it from scratch, just like you're looking at a 2D drawing and then you have to draw it yourself on your computer again. So that's just my thoughts on it, I guess.
Yeah, it is one of those things that does have a lot of like challenges to it, I suppose, and how to be legally responsible for something that's like that and how to translate that information appropriately to the people that need to see it. you know, because again, if you say you stamp a 3D model that has all that information, the person that wants to look at that 3D model, they'd have to have the software to look at it, to open it up. And then there's the time factor. Say you stamp something that's 10 years old. 10 years from now, who knows if that software even exists anymore and how to open that stuff up. But you can always print a piece of paper and have a piece of paper sitting there for 20 years. You know, you can always see that. So there's a bunch of challenges as far as that goes, for sure.
Totally, yeah. And then responsibility as well. Like, what if you stamp it and someone tries to change the 3D model somehow? There's also that aspect where it's like PDF or like a paper is set, I guess.
Yeah. Yeah, I guess we got 5 minutes. Is there one last question we could get? Otherwise, I'd be handing it back to Dr. Driver.
All right. Well, thanks everybody for coming, and thanks to our presenters. That was a really interesting and definitely not your typical connection that we had a little case study on. So that was quite interesting. I just want to draw your attention to the screen, or I guess it's to Dean's shared screen. The Steel Center has been around for 5 years now, and you can see our members. I just want to make sure that I give a nod to the supporters, and you can see Steadfast Engineering as one of them. We're really, really happy to have Steadfast as one of our members. They bring to the table a skill set that's just a little bit different from the other members. So that's what we're looking for, diversity. If you're with a company who is not on the screen and you're interested in joining the network, please let me know, and I'd be more than happy to talk about that, of course. So